right, we are going to wrap up 5.1, kind of how we started, and we're going to look at some more examples that involve one of the direct applications of basic exponents, which is units. And it's a common issue. Like, I have students in calculus courses that will put the wrong units on volume answers or area answers. It happens a lot. So suppose we're working in inches on part A, and we want to first remember that it says the volume of the cylinder is the area of the base times its height. So let's just say we have in general some sort of width times the length times the height here. So now suppose we were working in inches. So what would that volume, being the length times the width times the height, if the length is in inches, we would have L inches times, if the width is in inches, it would be whatever the width is in inches, times whatever the height is in inches. So just as we talked about in our opening examples, we think about the length times the width times the height times the inches times the inches times the inches, and we end up with our length times width times height, but that inches times itself 3 times is cubic inches. So when we work with, and this is what we highlighted at the beginning of the section, volume is always a cubic unit in its label. All right, so then for this particular example, we're just going to evaluate something. It says if the object is this rectangular solid now with a square base, looks like I need a space there, whose height is twice the base and the base length is 3y, what is the expression for the volume? So let's go ahead and just kind of sub this in. So our volume, it says, has a square base and the base length is 3y. So we're going to have 3y times 3y. So that's our base length width, if you will, but it's a square, so side times side. And then times, it says the height is going to be 2 times the base. So we can think of this height here. Let me just highlight that. So it says the height is twice the base. So my height is going to be twice what one of those base lengths is. So the 2 times the 3y would of course be a 6y on that. Okay, so I now have, in terms of base times area of the base times the height, so 3y times 6y. And so multiplying those out, we are going to end up with the 3 times the 3 is the 9 times the 6 would be 54. Y times y is going to be y cubed. And then we've already discovered that our label here would be cubic inches. So that would be our final answer. And then part C just says, let's actually evaluate this volume if the y variable here was equal to 2. So now let's just sub in 2 for that y. So we would have 54 times 2 cubed. So 54 times 2 cubed is 8. And so that comes out to be 432. And again, we discovered in part A, our label is cubic inches. All right, so let's look at another one. So this one's going to seem significantly more complicated, and maybe the concepts are a little harder, a little different, maybe something you just haven't encountered, let's put it that way. So there's some formulas we're going to talk about just kind of from, like you might see them in a science class or something, but we're not so interested in the formulas. We just want to really work with units in a way that is going to reflect how we work with variables. So it says weight density is defined to be weight per volume, or weight divided by volume. So a common label would be weight in pounds, volume, cubic measurement, so maybe cubic feet. So pounds per cubic feet is a common label for weight density. Then we go on to say if fluid pressure is defined to equal weight density times depth, what would my label be? So again, this is something that I have come up in a calculus class, and I will have students give the wrong label for fluid pressure. So fluid pressure is going to equal weight density. So we just said that from up above here that a common label for our weight density would be pounds per cubic feet. So this would be pounds per cubic feet. And then times depth. So let's just think about, depth. If you went down to, the bottom of a pool, how would you describe that depth? If it was 7, what would it be? Feet. Okay, so the depth here is just feet. So your depth units, so you multiply units just like you do variables. So if I think about, I have feet divided by cubic feet. And so if I think about this, let's expand this out for a second. So I would have pounds times feet divided by feet cubed is really feet times feet times feet. So what do I get to do? I get to reduce feet over feet, one of those factors. So this just goes back to kind of a basic reducing here with units. And I'm left with pounds, and then in the denominator, feet times feet, so over square feet. So this would be the unit or the label for fluid pressure. So when we think about that, that can help in a science setting. It can help us to interpret then what fluid pressure might mean. So if fluid pressure is equal to pounds per square feet, let's think about what pounds is a measure for. Well, pounds is a measure for weight. We weigh ourselves in pounds. And square feet, remember from our opening discussion, a square unit is an area. So fluid pressure is something that describes the weight per area. So that's how we could maybe interpret that. So it's just realizing how some of these really basic algebra exponent ideas can be extended to units. I think that's an important thing to see in your relate to like your science classes as well.